we can calculate the density of air. So temperature, we have to calculate absolute temperature. For that, for the given degree centigrade temperature, we convert it to the absolute scale. So that is 298 K is the temperature. And the gas constant for dry air, based on the molecular weight for the gas is 29 kilogram per mole at 3 megapascal, so that we can calculate the gas constant. So R is equals to R bar divided by molecular weight. MW is molecular weight. So that R bar is given as 8,314 joule per kilomole Kelvin. That is for the air. Therefore, by calculating that, we can get 287. So this 287 is the gas constant R for air. So using the perfect gas law, P is equals to rho RT. Rho is density of air, R is the gas constant of the air, and the T is the absolute temperature. So that from that we can calculate. So P is already given. So density is equal to P over RT. So that means what? P is 3 times 10 to the power of 6 Newton per meter square, SI unit. You have to convert this megapascal into SI unit, so that it is megapascal means 10 to the power of 6, and Pascal means Newton per meter square. So by dividing this to R is 287 and T is 298, so that you can find 35.08 kilogram per meter cube. So this is a special case actually. The pressure, static pressure given is too much high when I compare it with the atmospheric pressure, because atmospheric pressure is 0.101 times 10 to the power of 6 or 0.101325 megapascal. But this is 3, so that is high pressure. That's why the density also considered high here. But the actual density of air is nearly 1.225 kilogram per meter cube. It is not as such 35. But this is a special case for the dry air at 3 megapascal. Okay, so let's come to the first law of thermodynamics. So the first law of thermodynamics is the statements of conservation of energy. As I told you, there are conservation of energy, conservation of momentum, and conservation of what we call that? Energy conservation, momentum conservation. Again, another one conservation principle there, or mass or continuity. Mass conservation. So that from the energy conservation, we have the dq plus dw is equal to de. No, this is delta q. Q and W are represented with delta. Why? They are called pass property. Q is the heat added to the system or heat rejected from the system, heat in or heat out. That is Q. And delta W indicates the work done on the system, or it can be the work done by the system. Look, there are two types of terms. When heat is added into the system, the heat gains positive sign. When the heat is out from the system, then it is with negative sign. Similarly, delta W, that is the work done, can be either the work done by the system or the work done in the system. So during these two different conditions, there will be plus or minus sign will come. Okay, so the integral dq, delta q plus delta w are the having fast property. But this is differential form. dE is differential form, so they are different. The representation also different. so that you have to identify these two quantities. So energy conservation principle by itself states that energy can be neither created nor destroyed, but it can only change in the form from one state to another state. That is the meaning of energy conservation. So the first law to the fluid moving through the fixed control volume. So look, this is the way you have a fixed control volume here. Okay, so the control volume B is having control surface S. So this is a finite control volume fixed in space. So the fluid is moving through it. The fluid is coming in and out through the finite control volume. So the control volume is fixed in the space and the fluid is moving through it. In the second case, you can see the finite control volume itself is moving with the fluid. Finite control volume by itself is moving with the fluid itself. So two different approaches that we can use here. So V is moving also, the volume, the fluid also moving. So moving fluid is moving control volume. So these approaches are some of the approaches that we can use, finite control volume approach. The second approach is infinitesimal volume approach. This is finite volume. Another is infinitesimal volume approach is there. And there is also the third one is molecular approach. And the molecular approach is more of atomic level, molecule and atomic level. That is highly sophisticated type. That is beyond the capacity of this course. So we might emphasize for the finite volume approach or infinitesimal small volume approach. So that is what. So in the case of first law of thermodynamics, dq is related to this rate of heat added to the fluid inside control volume from surrounding. Here, rate of heat added. So that's why it is here positive. The second delta W is rate of work done on the fluid inside the control volume. Work done on the fluid inside. So it is work done on the system. Therefore, it is taken positive. If work is the rate of work done by the fluid, if it is by the fluid, then this thing is negative. Okay, which is equal to rate of change of energy of fluid as it flows through the control volume. So dE is the internal energy we call. It is the rate of change of energy of the fluid as the fluid flows through the control volume. Okay, so that is the meaning of this equation. You can simply equate these three variables in this form. Okay, so this is the meaning of first law. Look, delta U is equal to Q minus W. Look, delta U is the internal energy, like here, dE. Again, Q is the heat added to the system and work done by the system. Okay, so work now here, work is done by the system, not work done by the fluid. Here, in the previous case, you can see rate of work done on the fluid, on the system. Work done on the system is plus, but here, work done by the system. W, work done by the system, so that it is with minus sign. Okay, so this is a simple representation of first law of thermodynamics. Okay, that is called law of energy conservation. Okay, so you have some symbolic representation here. So this is a connecting rod cylinder mechanism. Okay, here you can see the heat, the recycling of heat, and the This symbol simply shows you the change in internal energy. The change in internal energy. So the change in internal energy of the system is equal to the heat added to the system minus the work done by the system. Or the change in internal energy of the system is equal to the heat added to the system plus the work done, the work done on the system, not by the system, but on the system. Okay, so these are the meaning. So delta U is representative of dE here. Q is representative of delta Q, and W is representative of delta W. So this delta W can be plus or minus as I told you. So in energy conservation, the total energy of an isolated system remains constant. That is the conservation principle. It is just change form. It can change form from one form to another only. Delta U is internal energy. So that is total energy contained within the system. Within the system, like molecular motion, potential energy, that are internal energy. Or it can be kinetic energy. Okay? So they are internal energy. Q is heat. Just it is energy transferred to the temperature difference. That the temperature difference helps to flow the media from hot media to cold media, right? So positive for heat in and negative for heat out from the system. When heat is in, it is positive. When heat is coming out, it is negative, right? Again, W is the work. So this work is energy transferred by forcing acting over the distance. Force acting over the distance. So force times distance gives us work. So work done is equal to force times distance, as you know. That means by displacing the cylinder to the top dead center to bottom dead center, the work can be done there. So this work done is positive for work on the system. When the work is done on the system, it is positive. And when it is negative for work by the system. When work is done by the system, it is negative. This is conventions. System and surrounding. Whenever we are talking about thermodynamic system, a system is a collection of any number of systems, subsystems, right? So system and the surrounding are the part of universe. You can say the first of universe under our consideration, that being studied. And while surroundings are everything else, energy change between them, which is measured by Q and W. Okay, so look, this delta Q is the integral of delta Q from point 1 to 2 is not directly equal to Q2 minus Q1. In your mathematics, dq from point 1 to 2 is Q2 minus Q1. That it doesn't obey because it follows the path, okay, for the closed path only. But this is the energy part, internal energy, which is directly you integrate it from point 1 to 2. It is E2 minus E1. So the formulas are not applicable for this one. Okay. The application of first law to closed cycle is balance between the heat and work exchange in the cycle process. So in the cyclic process, dq is equals to dw only. The internal energy part is taken as actually the internal energy part is taken as constant. So the process in such case, the process when the process is adiabatic, in adiabatic, change in heat is equals to 0 because it is constant. Q is constant, so that change in Q is equals to 0. And if there is no mechanical exchange of work, or if there is no shaft work, the delta W is equal to 0. And the energy of the system remains also constant. So E1 is equal to E2 in such case. Okay. So adiabatic process is a type of thermodynamic process that occur without transferring heat. So adiabatic process means what? dQ or delta Q is equals to 0. Or mass between the thermodynamic system and its environment. So that another is second law of thermodynamics. So once we understand first law, the second law of thermodynamics is it states that in any process, in any spontaneous process in the closed system, the total entropy will increase. That means it is just natural process moving towards to the state of greater disorder. That means always heat flow from hot object to cold object. That is natural process. But in some cases, you may have a condition of heat transfer from cold to heat, like in the case of refrigerator. For such process, we need other energy source, the energy which pushes that. Okay, so that is a special case. Okay, so the second law of thermodynamics states that heat cannot move from reservoir of low temperature to a reservoir of high temperature in a cyclic process. So this implies that heat spontaneously flow from hotter to colder object. That is the meaning of thermodynamics second law. So, for example, this is the flow pattern, hot to cold. That is natural process. For that, you can consider the ball having such kind of bowl. On the bowl, if you put ball at the top of this thing, immediately the ball falls down to the valley here, from the peak to valley, obviously. That is natural process. But if you want to transfer this ball at the lower level to the higher position, you need some extra energy to push it to upward. Like that, in the case of thermodynamics, to transfer cold to hot, what is required? Extra energy is required to push, in the case of refrigerator, actually. Okay, so that is what we call second law of thermodynamics. Actually, we have zero law also, zero law of thermodynamics, so that it has no importance. In ideal condition, the entropy of the system is equal to 0. But in actual condition, entropy is always greater than 0. That is natural. That is, there is a disorder of system. Whenever there is some thing happen, there is a disorder of environment. So that is entropy. So that is here. So what are the key concepts of second law of thermodynamics? One is entropy. So entropy is a measure of disorder or randomness in the system. And the second law of states that total entropy of the universe is always increasing. That means it is always positive number. Look, delta S is greater than 0 means what? Some number greater than 0 means entropy is always positive. Okay, so the total entropy of the system is always increasing so that it is greater than 0 or positive value. Heat flow, the Q, heat will naturally flow from regions of higher temperature to lower temperature. That is also another statement of second law. Okay, entropy is one, heat flow is also the second. So to move hot heat from cold to hot region, external energy must be used. In the case of refrigerator, we need external energy for that. So based on that, the energy conservation conversion efficiency always less than 100%. It is, according to the second law, the efficiency is always less than 100%. Why? Because there are a number of losses in the system. So the second law sets the limit on how efficiently heat can be converted into other form of energy like mechanical work. So no engine can be 100% efficient naturally. And some energy always be lost as a waste heat because of friction, because of heat dissipation, and so on. So that is the key concept of second law. So the second law of thermodynamics introduces the absolute temperature scale and the enthalpy. So no, the entropy. So the entropy and absolute temperature are related in this condition. TDS, T is absolute temperature, DS is the entropy, which are always greater than or equal to dQ. So Q is the heat. So maybe this process can be a reversible process and it can be also irreversible. If the flow is only in one direction, then that is irreversible process. And if the flow is reverse itself, then it is a reversible process. So in this equation, equal sign greater than or equal is there. So the equal sign indicates that it holds for reversible process. So so the concept of irreversibility is related with frictional loss, viscous dissipation, shock waves in supersonic flow. So these are also there. So due to the presence of this, the process is irreversible. In reversible work done by the system per unit mass is dW of reversible is equal to PdV. P is the pressure, dV is specific density or specific volume. Okay, it is 1 over density. V is specific volume. Specific volume means 1 over density. To clearly state this thing for you, let me take some pointer here. We have this relation. Pressure is equals to rho, density rho, R T from the gas law. This is one of the equation. So this density, but specific volume, small v is equals to 1 over density. So this equation means what? P is equal to rho RT indicates P over rho, density of rho is equal to RT. Is equal to RT. Okay, so if I substitute 1 over rho by V, PV. So finally from this what we can get, okay, PV is equals to RT. That is one of important formula for us. PV is equal to RT. So this V is called the specific volume. That is 1 over density. It is density is mass over volume, but this is volume over mass. Therefore, it is called a specific volume. Okay, so this V is specific volume. So PdV is pressure times specific volume. Okay, so work done by reversible work done by the system per unit mass is like this. So Another, we'll see the Gibbs equation. The Gibbs free energy and the Gibbs equations are useful for us to describe the combination of first law and second law of thermodynamics. Okay, so from that we have TdS is equals to temperature, entropy is equals to dE plus PdV, and this PdV is the work done actually. dE is the internal energy, okay, and the PdV is the work done. So temperature times entropy, the change in entropy gives us this kind of equation. So now we are defining another thermodynamic constant, which is enthalpy. Enthalpy H is another thermodynamic property. So that enthalpy is equals to E plus PV. E is internal energy, PV is the work done by the system, okay? Or work done by the reversible system. So E is internal energy,